All right, let's get right into it. We're talking about something pretty amazing today, the world of medical implants. Where high-tech engineering literally meets our own biology. Now, you'd think it's simple, right? You put something helpful into the body, and the body says, great, thanks. But it's not that simple. It's actually a microscopic war zone, and scientists are having to completely rethink the entire rulebook. And that brings us to this really strange paradox. Think about it. Pacemakers, artificial hips, dental implants. These things are designed to save our lives, or at least make them way better. But for some reason, our immune system often looks at these helpful devices and sees a threat, a hostile invader. So the big question is, why? Why does our body try to build a wall around the very things that are supposed to heal it? And this is not some tiny niche issue we're talking about. It's estimated that a full 10% of the population in the US alone has some kind of medical implant. We're talking tens of millions of people. So their health really depends on figuring out how to win this biological tug-of-war. Understanding this is, well, it's absolutely crucial. So for decades, this was the gold standard. This definition, which is from way back in 1987, basically says that if the body doesn't freak out and violently reject an implant, then, hey, it's biocompatible. It's a really passive idea, Just don't cause a huge problem and you're good to go. But as we're about to see, not causing a problem is a really, really low bar compared to actually helping the body heal.
Okay, so it's time to meet the main villain of our story, the foreign body reaction, or FBR. This is the body's universal hardwired defense system. It's what your body does against any foreign object it can't absorb or break down. Doesn't matter if it's a tiny splinter you get in your finger or a super advanced life-saving implant. The reaction is the same.
The body's strategy here is actually kind of brilliant in its simplicity. If you can't get rid of it, you imprison it. It just starts building this thick, tough wall of scar tissue, it's called a fibrous capsule, all the way around the implant. The goal? To completely cut it off from the rest of the body. It's basically a biological quarantine. And this whole siege operation, it's not random. It's a very precise 5-step process. It all starts within seconds, literally seconds, of the implant going in. Your blood proteins swarm the surface, basically painting a giant target on it. That triggers the first alarm, acute inflammation, which brings in the first wave of immune cells. From there, it escalates to chronic inflammation as the real heavy hitters arrive. They'll even fuse together to form these huge, giant cells to try and eat the invader. And only when all of that fails does the body go to its final option, building that prison wall.
So what does this prison wall actually do? Well, its effects are devastatingly practical. That scar tissue isn't just sitting there. For a pacemaker or a brain implant, it acts like an insulator, blocking the electrical signals. For a device that's supposed to release medicine, it traps the drugs inside. For something like a glucose sensor, it completely blinds it. This foreign body reaction, it's the #1 reason that so many of these incredible medical devices eventually just stop working.
So, who's running this whole operation? Who are the masterminds behind this siege? Well, it turns out it all comes down to one specific type of cell, the macrophage. Think of them as the immune system's first responders. But here's the twist. They can act as both the demolition crew and the construction crew. They are the key players that ultimately decide if an implant lives or dies. And this was the huge breakthrough. Scientists realized that macrophages aren't just one thing. They have 2 different faces, 2 modes. On one side, you have the M1s, the attackers. They're pro-inflammatory, their job is to destroy invaders, but they cause a ton of collateral damage. Then you have the M2s, the rebuilders. They're anti-inflammatory. Their job is to calm everything down, promote healing, and help rebuild tissue. The whole game comes down to the balance between these two. Too many M1 attackers, and you get that fibrous prison wall every time. Realizing this didn't just tweak the old way of thinking, it caused a total revolution. The old goal was to make stealth materials, things that could just hide from the immune system and hopefully go unnoticed. The new goal is so much bigger. It's to create materials that actively talk to the immune system, materials that can persuade it to switch from attacking to rebuilding. It's a huge shift, from hiding to actually collaborating with the body. And this has given engineers a completely new playbook. They're not just thinking about what a material is made of anymore. Now they're thinking about its physical shape, its texture, things like how porous it is. They're designing implants that can slowly release specific molecules, like anti-inflammatory drugs, to calm down those M1 macrophages. And they're engineering the actual surface chemistry to be less alarming to the body when it first arrives. And here is a perfect example of this new playbook in action.
It's incredible. Researchers found that if they just changed the physical structure by creating these uniform little pores exactly 40 micrometers wide, it completely flips the body's response. Instead of seeing a solid fortress to attack, the body sees a scaffold, a structure to grow into. It becomes a kind of cellular playground. This encourages blood vessels to grow right into the implant, and that fibrous wall gets dramatically smaller.
So, what's the big picture here? What does all this mean for the future? Well, we are on the verge of a new generation of medical devices that don't just exist inside of us, but actually merge with our own biology. And that is going to lead to breakthroughs we've only been able to dream about until now. Just think about brain-computer interfaces. I mean, the biggest hurdle, the ultimate challenge, is the foreign body reaction. In the brain, this process creates something called a glial scar. It's basically the brain's version of that fibrous capsule. And this scar wraps around the electrode, insulates it, and over time, the signal just fades away. So if we can solve the FBR, we can create long-lasting, crystal-clear connections between our minds and machines. It's the key. Which brings us to a whole new, evolved definition of biocompatibility. It's not about being passive anymore. The new idea is right here. It's about active guidance. The goal now is to create a material that can trigger and guide a very specific positive healing response, one that leads to functional integrated tissue with its own blood supply. The implant stops being a foreign object and starts being a catalyst for regeneration. And this massive shift, from just hoping for passive acceptance to actively guiding tissue integration, it leaves us with a really deep question. If we can design an implant that becomes so interwoven with our own living tissue, that blood vessels grow through it, that our own cells call it home, well, where does the device end, and where does the body actually begin? We're heading towards a future where healing isn't just about fixing a part, but about truly becoming whole again.